Welcome back everyone to this lecture series on tensor operations. We're going to be covering things like indexing and slicing, reshaping tensors of tensor views, as well as tensor arithmetic and basic operations. In part 2, we'll expand on this to dot products, matrix multiplication, and some more advanced operations that we won't really see throughout the course that often, but just in case you end up using them, we'll go ahead and show you how it's done. Okay, let's go ahead and jump to the Jupyter Notebook and get started. Alright, I've already gone ahead and imported Torch and NumPy as NP. The next thing I'm going to do is quickly review indexing and slicing with a tensor. And it actually performs and behaves the exact same way as indexing and slicing with a two-dimensional NumPy array. So first, let's actually create a two-dimensional tensor. We'll say torch, arrange, and let's go ahead and say arrange 6, and then we will reshape this to be 3 by 2. And let's say x is equal to that. So if I take a look at x, I have a 3 by 2 of the numbers 0, 1, 2, 3, 4, 5. And then let's imagine I wanted to actually grab a single individual value from this. Well, just like a two-dimensional NumPy array, I simply need to pass in my row index, comma, and then my column index. So for example, to grab the number 3, that's at row index 1 at column index 1. So then I would say 1, comma 1, and just like a NumPy array, we get back to 3. Notice that we actually still get it back in the form of a tensor with holding a single scalar value. We actually don't get back, if we check the type of this, just a number. So keep that in mind. Even though you may be indexing, it'll still return back these PyTorch tensor objects. Now if we wanted to grab slices, we can do that as well. So for example, I can say colon, comma, 1, and that says grab every row from column 1, essentially all these values in 1, 3, and 5 there. So we go ahead and run that, and we get back 1, 3, and 5. Now you may have noticed that by just asking for column 1 here, we get back all the values. However, we don't actually retain the fact that it was a column. So we get it back as a 1 by 3 instead of the original 3 by 1. So we don't get that vertical, instead we get it back horizontal, just a list of values. If for some reason we actually want to retain this sort of vertical column, so we actually want this singular column as a 3 by 1, so I want 1, then 3, then 5, then the way I do that is instead of just requesting 1, I request it as a slice, so I can say starting at 1, go ahead and go all the way to the end, run that, and then we get back this column value. Okay, so here we're just indexing for that column, here we're actually slicing for that column. Now next what I want to show you is how you can reshape tensors with .view. So view and reshape, those two methods do very similar, essentially the exact same thing, by returning a reshaped tensor without actually changing the original tensor in place. So there's a link in your notebook that has a really good discussion on the differences between view and reshape. But for our use case, what I'm going to do is just quickly show you the difference by running view and then running reshape. So let's go ahead and say x is now equal to torch arrange. We'll say 10 here. So right now I have 0, 1, 2, 3, all the way to 9. Now if I wanted to say x dot view as a 2 by 5, then I get back those same values. However, now I'm viewing it as a 2 by 5. I have 0, 1, 2, 3, 4, and then 5, 6, 7, 8, 9. Now take a look at just x again. Notice I simply viewed it in that shape. I didn't actually call reshape on this. If I say x dot reshape 2 by 5, and I run this, now this is returning this shape of 2 by 5, those same values, and then when I take a look at x, that is still not actually changing it. So view and reshape, they're actually extremely similar. And again, if you take a look at our notebook, so if you bring up the notebook here, and you can see the section where we're talking about reshape tensors with .view, they're extremely similar methods, and the technical details of how they're different depends on whether or not they're actually changing the object in memory. So there's a link here that's a really good discussion on differences. So I would recommend you check this out. It basically shows you the link and a full discussion. And this changed depending on what versions you're using. And right now, you don't have to worry about it because we're in post 0.4. So all of this is still true here. But there's a really good discussion on differences between .reshape and view. Essentially, view existed for a really long time, and then they added in reshape because reshape is what's used in NumPy. People are really used to that. And essentially returns a tensor of the same data and number of elements, but with the specified shape. What you should be concerned with is whether or not you're changing the original. And the way to make sure you're changing the original is to simply say something like x is equal to x dot reshape, and then whatever shape you want. And then when you call x, it will have been now reshaped. So that's the main point to get across, that regardless if you end up using view or reshape, if you want to make sure that you're actually changing the object in place, just go ahead and do that reassignment. Now, something to keep in mind when you're working with the .view method is that views reflect the most current data. So to show you what I mean by that, I'm going to go ahead, take x, and then recreate those original values. So we'll just go ahead and redefine it again. We'll say x is equal to torch.arrange 10, run that. We see x here, and then we can verify x's shape that right now it's just 10. All right, so let's go ahead and say x.view 2 by 5. I see here now it's 2 by 5. I look at x hasn't been changed. But let's go ahead and take z and set it equal to that 2 by 5 view. So now if I take a look at z, it's 0, 1, 2, 3, 4, 9. But remember, views are going to reflect the most current data. That essentially means that z is now linked to x. So that means if I were to take x at 0 and set it equal to, let's say, 9,999, then take a look at x has changed. But now if I take a look at z has also changed. So when you're using view, keep in mind that we're actually reflecting the most current data. And when we're working with neural networks, that's actually a convenient property. So you'll see how that comes up later on. Specifically, when we begin working with artificial neural networks with both categorical and continuous feature data. Now, views can also infer the correct size, which is again really important since often we're passing in batches of information and we want to have the flexibility to change that batch size. So by passing in a -1, PyTorch will infer the correct value from the given tensor. So let me go ahead and show you what I mean by that. Let's go ahead and redefine x again. So I'm just going to scroll up here and copy this command again. So we'll say x is equal to torch arrange, x here. So often you're going to be dealing with tensors that are huge and you have to think of the shape. So you'll say x.shape and then it'll give you some sort of dimensions. And what we can do is say x.view. And let's say I want to view this as a 2 by, and I don't even want to bother figuring out what the other dimension should be so that it lines up with 10. What I can do is say -1. And what this is going to say is PyTorch is going to try to infer what the second dimension should be. So here we have the first dimension, which is going to be 2. If we pass in -1, it's going to infer that. So it basically inferred that it should be 5, since 2 times 5 is equal to 10. Now keep in mind, it's not going to be able to infer something that doesn't make sense. If, for example, we pass this in as an 11, notice now we have 11 numbers, 0 through 10. Since we're including that 0, that makes 11 total digits, which means the x shape is now 11. And if I try to infer what this should be, I'll get an error because a 2 by -1 is invalid for an input size of 11, which makes sense because 11 is not evenly divisible by 2. But if I change this back again to 10, everything works out just fine. So this -1 is really useful for when we're dealing with things that we just want to infer what that size should be. And keep in mind, you can use this in any dimension. I could say -1, 5, and it's going to infer that this should be 2. Okay. Now the last thing I want to go over is a little bit of basic arithmetic with tensors. So things like adding, subtracting tensors, multiplying tensors. And again, as always, we have lots of useful information for you in the corresponding lecture notebook. So if you open up that corresponding lecture notebook right now would be on the tensor arithmetic section. The thing I want to point out is if you scroll down, we have a table of the different operations, their underlying function, and then a description. And most of these are self-explanatory things like addition, subtraction, absolute value, square root, etc. So I won't go ahead and go through all of these. Instead, I'll just go through arithmetic to show you the different forms it can take, and then you can expand those ideas to all these operations here. Okay, so let's go ahead and bring that back up. What we're going to do here is create an A tensor. So I'll say A is equal to torch.tensor, and we'll say 1, 2, 3, and I went ahead and just made those floating point values. And then we'll say torch.tensor, and we'll say 4, 5, 6. So if I take a look at A, I have 1 dot, 2 dot, 3 dot. So again, the D type is floating point. And if I look at B, I have 4, 5, and 6. So as you may expect, the simplest way to actually add these values together, element by element, is just say A plus B, and it'll return back the result element by element. So it'll take the matching index position. So at index 0, we have 1 and then 4. So then the result at index 0 is going to be the addition of those two. 1 plus 4 is 5, and so on. Then we get 7, 3 plus 6 is 9. So another way we can do it is saying plus here in Python. What's actually happening is it's calling this underlying add functionality, and that's just basically the same thing. We could say add A comma B together, and it would add those two. So when you actually call this plus sign, PyTorch underneath actually calls this formal function adding. And this actually works the exact same way in NumPy. If you were to add two NumPy arrays together, there's actually some underlying kind of formal or official function for that particular process. The last thing I want to show you here is if you actually wanted to change the tensor in place. So there's two ways of doing this. The simplest way is just say A is equal to A plus B. But sometimes you see this formally written out using the underscore methods. So the underscore methods actually change stuff in place. So you can say A dot, and if you call add, you'll notice that there's two add functionalities. There's add and then add underscore. And you'll notice that this actually goes for all the functions, or all the arithmetic functions. You can see .mul, which would be multiply. If you hit tab here, there's two, mul, and then mul underscore. So let's go ahead and see what happens when we say a.mul and then pass in b. So what do you think is going to happen here? Recall we have our originals, 1, 2, 3, 4, 5, 6. So we run a.mul, the result is 4, 10, and 18. That makes sense because 1 times 4 is 4, 2 times 5 is 10, and then 3 times 6 is 18. Now if I take a look at the original value of a, the original a remains unchanged. If for some reason you actually wanted to perform a reassignment along with this operation, you have a couple methods. You could either say a is equal to the result of a.mulb, which would be the same as saying a is equal to the result of a times b. So these two are the same. Or what you can do as a shorthand, and you see this sometimes in the code and documentation, which is why I'm going to point it out here, is you notice, again, every arithmetic method had an underscore method with it. The underscore method will actually then do the same thing as reassigning this. So we can say a is going to be reassigned to the result of a multiplied by b. So that's the same thing as doing something like this. A is equal to a times b. So when I run that, I don't see any difference here, but then when I ask for a, notice it's now been permanently reassigned. And that's going to be what that underscore operator does, which is why there's kind of two of every basic arithmetic method. Okay. Coming up next, what we're going to do is we're going to talk about dot products, matrix multiplication of broadcasting, and a couple of advanced operations. Thanks, and we'll see you at part 2.